So hello everyone. So today we will be discussing about another chapter of organometallics. It's a very important chapter because we are going to discuss about metal carbonyls. So you must have seen the carbonyl ligand in many of the complexes, and also there are some complexes, actually not some, quite a lot of complexes. Those contain only carbonyls as ligands. So those are called homoleptic carbonyl complexes. So where there is only carbonyls as ligand are there. Okay. So that homoleptic carbonyls are also prepared, can also be prepared from many of the D block metals, and also these complexes act as precursor for other organometallic complexes. So what is the property of carbonyl that makes it so versatile that it can bind to any metal and any type of symmetry and all of those? So there are some, first of all, carbon monoxide is a sigma donor and a pi acceptor. So it's a pi acceptor ligand. Okay. So we know that generally pi acceptor ligands likes to make bonds with low valent metals. So same is with metal carbonyl, like this carbonyls as well. So they love to make bonds with low valent metals, and also sometimes zero valent and sometimes negative. So oxidation states as well. So because they are pi acceptors, because when it gives, it's a very strong sigma donor and also a very strong pi acceptor. So it is giving its electron via sigma symmetric orbitals to metal orbitals, and then in change it is also taking up the pi symmetric orbitals of the metal to its pi symmetric pi star antibonding pi orbital. So that makes the bond even more stronger. So that is why, and that is the thing that why this carbonyls are, can be easily seen in many complexes, because they form very strong bonds with like many D block metals. Okay, and also there are a lot of spectroscopic techniques that you can easily get to know about the carbonyls, the type of bonding it is in with the metal complex. For example, first of all, the carbonyl you can get, you cannot get information from a proton, right? Because carbonyl has no H now, but you can have information about the carbonyl from 13C, right? And also you can have this C double bond O stretching frequency, which is very, very sensitive. It depends upon the type of bonding, in the metal center, and what is the, how strongly it is accepting the electron, or how strongly it is bonded to the metal. Everything you can get to know via IR spectroscopy, which plays a very, very important role in this metal catalyst, because you have that carbonyl peak distinguishedly, beautifully. You can see in the IR spectroscopy, and it will tell you about the metal complex and about how these carbonyls are arranged in the metal complex. So infrared spectroscopy is very important tool to judge any metal complex having carbonyls. So if you want to study the carbonyls in the metal complexes, then you can go for IR spectroscopy, right? And also sometimes you go for 13C. IR is the confirmatory analysis for carbonyls. So these are some of the homoleptic carbonyl complexes. So you can see that it can form bond with nickel, iron, chromium, manganese, cobalt, iridium, osmium. So these are all the examples of homoleptic metal carbonyls. Now, let us move forward and let us understand the structure and the pi bonding. And also, I told you that infrared spectroscopy we are going to discuss quite a lot, because that is the confirmatory analysis for metal carbonyls, and you get a lot of information from IR about the carbonyls. Okay, so let us first understand what is the structure, and let us talk about the MO diagram. So this is the MO diagram that they have given in the book, figure 3.2, and it's quite informative. From this MO diagram, you can easily get to know what is the binding pattern, and from where it is giving the electron, where it is accepting the electron. So ligands, in the ligands, whatever is the homo, that electron is given to the metal, and whatever is the LUMO, so on that orbital, the metal gives back the electron. So you can easily see that since carbon is a pi, except it's a vacant, the LUMO is a pi star. So definitely, when it is pi, when it is accepting its electron from when it is accepting electron from metal to itself, then it is having it here in the pi star, and when it is giving as a sigma, so it is giving as a sigma. right? So in this case, sigma is higher in energy than pi. So you cannot say that pi is giving the electron. No, sigma is giving the electron. Many people actually get confused because many a time we have seen that sigma is more stable, so it is lower in energy and pi has to be here. No, but if here it is sigma donation and then it's a pi exception, acceptor kind of a ligand, right? Okay. Now you can also see that this orbitals are the atomic orbitals of carbon and this orbitals are the atomic orbitals of oxygen. You can simply see that this sigma, that is the HOMO and also the LUMO, they are actually kind of more closer to the energy of the atomic orbitals of the carbon than the uh, energy of the atomic orbitals of the oxygen. So what does this information mean? This information means a very important thing. It means that mostly the electron donation and acceptance is via carbon and not via oxygen. That is why you draw like this metal and you draw CO and you don't draw OC, right? Because it is mainly because of by the carbon. So that sigma bond, that is the HOMO and the LUMO has more C character. Okay, more percentage of like so C than oxygen. Let us read what is written in the paragraphs because that is also very important. Now, the properties of carbonyl as a pi acid ligand, that is the pi acceptor ligand. Pi acid, we mean that acid that means can accept electrons, right? So it can accept electrons in its pi symmetric orbitals. So that is why it is written pi acid ligand. As well explained by the molecular orbital diagram of carbonyl. The HOMO of carbonyl is a sigma orbital having a higher amplitude on the carbon atom. As I told you, it is kind of closer to the atomic orbital of the carbon than the oxygen atom and is therefore considered as a carbon-based orbital, which is also slightly antibonding in nature with respect to the oxygen atomic orbital. You can see, right? Generally, what we see is that there is atomic orbitals and then the sigma bond or any bonding interaction is that takes place between those orbitals of two different atoms that have lower in energy, that are lower in energy than both the atomic orbitals of both the atoms. So in that case, sigma should not be here. It should be over here, right? Somewhere like below oxygen as well, because it is the bonding character that is emerging from the both carbon and oxygen. Go more towards carbon, but it is happening because of both, right? So I think you will agree if I say that this bonding interaction should be lower in energy than the atomic orbital of oxygen. But you can see in this diagram, this is not the case. So what does this mean? This means that this sigma has more dominance of carbon atom than oxygen, and also it is some kind of anti-bonding with respect to the oxygen. Okay. That means for like what this means we are going to discuss later because it is very important and just for now you need to understand that it is kind of having some antibody character with respect to the oxygen atom. Okay, so this result we are going to use it further in this chapter in order to solve some questions. Now the pi star antibonding orbitals, which are LUMO, are closer in energy to the carbon atomic orbitals than the oxygen atomic orbitals and thus have a greater amplitude on carbon again, right? So this explains why carbon monoxide binds to the carbon atom and also why it is a good sigma donor and a good pi acceptor. Now there exists a strong back bonding or pi overlap of metal electrons to the pi star antibonding orbitals of carbon. That is why these carbonyls are so versatile ligands that we can bind with any d block elements it wants because the overlapping between the metal d orbitals and the carbonyl d orbitals, these pi star orbitals are very, very stronger. Now, most of the metal carbonyls obeys the 18 electron rule, and in case where it does not obey it, the carbonyls will be comparatively more reactive and will undergo reactions such as dimerization or electron abstraction to gain 18 electrons and many things. But you can see dimerization, for example, here in case of manganese, you can see that manganese needs, if you just consider this part of the complex, how much electrons are there in this? If you count, manganese have 7 plus 2 and 2. Well, there are 5 carbonyls, right? You don't have to consider this now. We are talking about like why it is dimerizing. So it is a 17 electron complex, okay? 10 from the 5 carbonyls and 7 from the metal itself. So it is a 17 electron complex, and such carbonyl complexes generally show 18 electron rule. But sometimes when it is lower than 18 electron, then what happens? Sometimes it dimerizes if there is space enough. Like if it was quite a lot of congested, then it would have not dimerized. But in this case, it is not that much congested. Manganese is not that small metal, and that is why it is dimerizing to form 18 and 18. It's one metal bond, so one electron is counted for both metal atoms. So that is the dimerization is happening. It's a way of completing the 18 electron. Also, dimerization is also dependent upon the size of the metal. I told you, right? If the metal was small enough, then the dimerization would have not happened, because that would be a lot of steric disturbances, which any metal does not want, or any creature in the earth on the earth doesn't want to be unstable. So everyone wants to be stable, and that is why this dimerization is highly dependent upon the size of the metal and also the number of ligands it can accommodate without steric repulsion. So steric repulsion is the biggest thing that metal complexes, they don't want to be in that phase, steric repulsion phase. So this is the reason why 17 electron species like vanadium is quite small, okay, that cannot dimerize, so doesn't dimerize, while another 17 electron manganese can dimerize to form 18, because you know that manganese is quite larger than in comparison to vanadium. Also, the direct condensation of vanadium and carbonyl is stable only in the carbonyl matrix at extremely low temperatures. Now, it has been found that carbonyl mainly shows two types of bonding. It is terminal or bridging. Okay, we have discussed in an previous chapter as well that carbonyl is a 2-electron donor. It is an N-type ligand because it is neutral. So it is giving 2 electrons all the time. Even if it has only 2 electrons to give. So even if it is terminal, it is giving 2 electrons, or it is bridging, it is giving 2 electrons. We can count as one metal to each, one electron to each metal, right? Whatever it is, you can count two max for carbonyl. So this bonding of carbonyl to the metal center can be of two types. It can be terminal and bridging. So all of this thing, like if whether the carbonyl is bridging, whether the carbonyl is terminal, you can get information from the spectroscopy, and that is IR. Okay. So as the CO stretching frequency is quite sensitive to small changes in the electronic environment, one can identify these by IR spectral studies. So in IR, you know what you study, right? You study the stretching frequencies between the bond. Now, the stretching frequency of the bond between the atoms. So if that stretching frequency is highly sensitive to the electronic environment of the metal center or the bond complex, then you can easily study anything, or basically the electronic properties of the by the IR, right? That is what you study in IR. That is what information you get from IR. So now, in electron counting method, to find out if the complex obeys the 18 electron rule, both bridging and terminal are considered as 2 electron neutral donors. I told you, right? And we have also counted a lot of electrons, like electrons with a lot of metals. So I think it is clear for now. Now, it is rather difficult to arrive at the number of bridging and terminal ligands by using just the electron counting methods. So since you know you only count the electrons for both terminal and for bridging, you count 2 electrons for carbon. So sometimes when you're counting just a copy and paper, you don't know if how many exactly carbonyl are as bridging, how many exactly carbonyl are as terminal carbonyls. So you need to know get information of all of these from some spectroscopy, right? So there is what IR comes into existence, because this in IR, you know, this when carbonyl is bridging, then it is binding to two metals. So in that case, the bi-accepting ability of the carbonyl is quite high, because both the metal is giving electron, right? So both the metal is giving electron, and that is why the carbonyl is accepting in its pi star from both the metal. So any electron is adding up to the pi star, then what is happening? The bond is becoming weaker and weaker, right? So if the bond is becoming weaker, then the force that means what? That simply means that the bridging carbonyl will have lower frequency, because it is you know that the frequency is directly proportional to the force constant, or we can say the bond energy of the bond energy. So if you are giving more electrons to the pi star, that means you're decreasing the strength of the bond, and that is why you're decreasing the frequency. So you will find that for bridging carbonyls, the frequency is quite low, and also the range is given you. So for bridging carbonyls, stretching frequency is observed in the range of 1850 to 1750 centimeter inverse, and for terminal carbenes, it is 2120 to 1850. Okay, for free carbonyl, you see it is even stronger. It is 2143, right? Now, okay. Now I think it is clear, right? Because what do you think? Like for bridging, it should be lower. The frequency should be lower because in case of bridging, more pi star or white electrons are there, and more electrons are accepted in the pi star. So that is why we're accepting electron in the star with the pi star. That means you're decreasing the bond strength, and that is why the frequency decreases, right? And then in case of terminal, that is also happening, but from one metal it is only happening, and that is why it is quite higher than the frequency. The stretching frequency is quite higher in case of terminal carbonyls than the bridging carbonyls. And when you have free metal carbonyl, that is when it is not attached to any metal, then in case you'll have more higher, even higher bond stretching frequency. It is around 2143 centimeter inverse. Okay. So there's one question, one very hypothetical question. For example, if any carbon is binding to a metal, which that metal cannot give back the electron. Like no pi accepting ability will work here because metal doesn't have electron to give it back to the carbonyl. So that means here in that complex, only carbonyl is acting as a sigma donor. So in that case, will the stretching frequency of carbonyl will be greater than the free stretching frequency of the carbonyl, or it will be greater than that or lower than that? So the answer over here is that it will be higher than that, because when it is sigma donating, because we studied that even the sigma, that is the homoorbital, is also anti-bonding, has some anti-bonding characteristic. So if the metal has like only sigma donation is happening, that means what is happening? Electron is removing from the anti-bonding characterized orbital. So that orbital that is having some anti-bonding characteristics, electrons is getting removed. That means the bond strength is increasing, right? So when carbonyl acts as only sigma donor, hypothetically, I'm questioning, this might also happen. Then in that case, the stretching frequency will be greater than the free metal carbonyl. I think there is some question in this book. I don't remember exactly, but if there is question, we'll be dealing with it. Otherwise, I think it is clear to you. Now, the bonding of carbonyl to a metal can be described as consisting of two components. The first component is 2 electron donation of the lone pair on the carbon, that is coordination exclusively through the oxygen is extremely rare into a vacant metal d orbital, and then this electron donation makes the metal more electron rich, and in order to compensate for its increased electron density, a filled metal d orbital can interact with the empty pi star orbital of the carbon ligand to relieve itself of the added electron density. Now, this second component is called the pi back bonding or pi back donation. Now, the two components of this bonding is called synergistic. Okay, more the sigma donation, then there will be more pi acceptance as well. Okay, so stronger, so more the pi donation by the carbonyl to the metal, the stronger is the pi back bonding interaction. So it is synergistic. Okay, now notice that although this involves the occupation of the pi orbital on the carbonyl, it is still a bonding interaction as far as the metal center is concerned. Okay, though the electron is getting added to the pi star, and you know that whenever there is electron adding to the anti-bonding, then what happens is the bond breaking takes place. But this interaction is really bonding. It's not breaking of the bond, it is forming of the bond, another bond, because it is with respect to the metal center. Okay. Now, there is a fundamental similarity between the nature of the carbonyl metal bonding and that of alkenes and acetylenes and phosphines and dinitrogen. So this occupation of the pi star on carbonyl does lead to a decreased bond order in the carbon monoxide molecules itself. That is true. That is why you observe lower stretching frequency for the free metal the free carbonyl than the metal carbonyl. Okay. Now the consequences that we might expect if the carbonyl bond order is reduced would be a lengthening of the carbon oxygen bond and shortening of the metal carbon bond. Definitely yes, because if you are giving the back donation, there is a bond is making, and that bond will shorter the bond. We know that double bond is smaller than the single bond, and that is why it's a kind of double bond, right? So metal carbon, the distance bond distance will be lower, and they, since the electron is getting added to the pi star of the carbonyl, that is why the carbon oxygen bond will become longer. Now, as the electron density on the metal center increases, more pi back bonding to the carbonyl ligands takes place. This weakens the carbonyl bond, that is when I'm talking carbonyl bond, that is means CO bond. Further, by pumping more electron density into the formerly empty carbonyl pi star orbital, now this increases the metal carbonyl bond stretching, making it more double bond character like, okay? Like that is the resonance structure would be like this, right? So more back donation, more stronger is this bond and more weaker is this bond. So that becomes more important. So this is the orbital overlap diagram. So it is the sigma and it is the pi. So this table is quite important. You can see like if it is carbonyl plus, then it is 200. I told you, right? If it is carbonyl plus, that is kind of like a only sigma donor, which doesn't exist all the time. So or we can say that is it does. So if it is carbonyl positive, that means that HOMO is also empty, right? So that is also having some antibonding character. So if you remove electron from that antibonding, the stretching frequency between the CO bond will increase. That is what is seen over here. It is more than the free CO. And when it is BH3, so it is also that is giving electron to the BH3 is a Lewis acid, right? So it is giving its electron, only sigma or no pi back donation is happening. I told you whatever I told you. So this is that example. Now this is also quite more than the free carbonyl, but lesser than the carbonyl positive. Why is it so? Because when we talk about carbonyl positive, that means we're talking about like really the electrons are gone now. But when we're talking about just the donation of the electron, that means there is an overlap, like sharing of the electron, and the electrons are not gone. So that is why the carbonyl positive is more has more stretching frequency. So you can see like, and also you can get to know about like how, because this like for example, this is, you will see that it is very high. The carbonyl frequency is quite high, even higher than the carbonyl positive. The reason behind it is that this metal center is positively charged. So if the coordination sphere is positively charged, that means the back donation is very, very weak. And that is why the this stretching frequency is quite high. Okay, when when the coordination sphere is negatively charged, that means the bimetal is quite heavy on electrons, and that is why the back donation will happen quite rigorously in such cases, and that is why the carbonyl stretching frequency will decrease, and that happens directly proportional to the number of the charges you have. So it is greatest for the 4 negative and smallest for the 1 negative. And also a similar trend is seen when you have positively charged thing, then you have lesser, and if you have 2 positive, then it is even more. So that happens. Okay, so let us move forward in this chapter. The stretching frequency of the carbonyl, the values is given in table 3.1. So it clearly illustrates the effect of charge and pair. So we saw the charge on the metal sphere is very important, and for the stretching frequency of the carbonyl, and thereby electron density on the extent of metal to carbonyl by bonding depends upon the charge, right? Although some additional factors such as electronegativity and size of the metals are being projected as influencing the electronic effect, but they are minimal. And what outcast them all is the charge. Okay, because all of these like electronic properties and electronegativity and size, they contribute less to the observed CO stretching frequencies. Now, the donor and the acceptor ability of the ligands on the metal has considerable effect on the absolute amount of electron density on that of metal. Now, this naturally affects the stretching frequency of the carbonyl, infrared stretching frequency of metal carbonyls when other ligands are present on the same metals. Okay, definitely. So, depending upon like what are the other spectator ligands, so this donating ability will also depend on the spectator ligands, right? If the spectator ligands is quite electron giving, then the pi back donation will be stronger. And if it is lesser electron donating, or we can say that electron pulling, or if it is even, it is also pi acceptor, then this pi accepting of the metal and the carbonyl will decrease. So, and also it depends upon the trans effect. There are quite a lot of effects, right? So ligands which are trans to carbonyl can have a particularly larger effect on the ability of the carbonyl ligand to effectively pi backdonate to the metal. So the two trans pi backdonating ligands will compete with the metal d orbitals, and we can see each other effective metal ligand pi backbonding. That is, I think it is clear. Now, if the ligand trans to carbonyl is a sigma donor, then it will increase the constant between the metal carbonyl constant will increase, more pi backdonation is happening. But if the trans ligand is a pi acceptor, then it will decrease the bond strength between the metal and the carbonyl. Okay, and that can easily be seen from the stretching frequency in the IR spectroscopy. Now, this table 3.2 shows the effect of a series of trans ligands on the metal carbonyl infrared stretching frequencies of FAC isomers of molybdenum, carbonyl whole thrice, and ligand 3. Now, pyridine and other amines are not very strong pi donors, and they are even worse pi back bonding ligands. So that is why the carbonyl has virtually no competition for the pi bonding, and it is that means that it is back donating quite a lot. That pi back donation between the metal and the carbonyl is happening quite high, and in the stretching, that is why the stretching frequency of the carbonyl will perhaps decrease for such ligands. You can see, right? But for example, PF3, they are strong sigma donors. All the phosphine ligands, they are very, very strong sigma donors, and that is why the stretching frequency is higher. So with each negative charge added to the metal center, very important line. So with each negative charge added to the metal center, the carbonyl stretching frequency decreases by approximately 100 centimeter inverse. It should decrease because more negative charge on the metal center, that means more high electrons the metal center is, so better pi back bonding it can show to the carbonyls, and that is why it will further decrease the stretching frequency. So it is given in general sense. So for each negative charge, there is decrease in the stretching frequency of the carbonyl by 100 centimeter inverse. It's approximate, okay? So the better the pi donating ability or poorer the pi accepting ability of the spectator ligands, the lower is the stretching frequency. So what things the stretching frequency of carbonyl depends on? It depends upon the metal, it depends upon the charge on the coordination sphere, it also depends upon the spectator ligands. These are following are the ranks of the pi acceptor abilities based on the infrared spectroscopy. So how do you know that which ligand is a better pi acceptor? So you can have all of these ligands one by one in the trans to the carbon, then you can easily find it out, right? Now, in addition to these two significant factors, the effect of electronegativity and size of the metal is also concerned, but we discussed that it is minimal. So the former has a marginal effect, table 3.3, and the later has no effect on the carbonyl stretching frequencies. You can easily see it is kind of very, very similar, right? So electronegativity of the metal does not really matter. Now, bonding modes of carbonyl. So there can be a lot of bonding modes. You can see carbonyl can bind maximum to 3 metals. Now you'll be surprised. How can a carbonyl bind to 3 metals? It does so. And in that case, its stretching frequency is even lesser. And also, this isocarbonyl coordination is kind of rare, but it is also seen. Also, there is asymmetric bridging is kind of like this. Asymmetric bridging is like kind of like this. Okay. This is semi-bridging. Sometimes like when this is happening, then this is happening. When this is happening, then this is happening. Terminal is quite straightforward. And also you can see different types of binding. And all these different types of binding will have different types of stretching frequency, and you can get the idea of different types of binding of the carbonyls to the metal center by IR spectroscopy. Now, different types of symmetrical and unsymmetrical bridging are observed within the bridging carbonyls. Among bridging carbonyls, mu2, that is the carbonyl that is bridged to two metal centers, are mostly often encountered, and it is noteworthy that mu2 carbonyl is not a dimetalloketones. No, it is a bridged carbonyl. The bond angle of M2CO is much more acute than the R2CO. Okay, and is also highly delocalized. Now, bridging of three metal centers or capping of the triangular face of polyhedron is also observed with many clusters of metal carbonyls. For example, radium 6, carbonyl 16, you find it out. You find that there are 4 mutual carbonyls are present in such complexes, and a variant of a bridging carbonyl is the semi-bridging carbonyl, in which the metal carbonyl metal bond is asymmetric rather than symmetric. Now, these can be considered as being intermediate between the terminal and the bridging carbonyls. Okay. In some unsymmetrical form called the sigma pi bridge, carbonyl acts as a 4 or a 6 electron donor, because here you can see now this carbonyl is giving 2 electron to this metal, right? And also this metal it is giving 2 or 4, right? So total how many electron it can give? 2, 4, 6, right? So carbonyl acts as a 4 or a 6 electron donor and shows a side-on coordination similar to the coordination of the vinyl ligands. Now, isocarbonyl coordination, though the carbon atom of the coordinated carbonyl to metals such as um, titanium, aluminum, and the lanthanides is also observed, but very, very rarely. I told you, right? The typical stretching frequency of the carbonyl ranges of neutral metal carbonyls are given in figure 3.4. Now, we'll be talking about the symmetry of the metal carbonyls in the next lecture. So we'll be starting with the symmetry of the metal carbonyls. We'll study various symmetry elements over here, not much, very little. And then we will be studying about the synthesis of the metal carbonyls, how metal carbonyls you can prepare, because this metal carbonyls acts as precursor for many complexes. So you must know how they are prepared in the industries. And also there are quite a lot of techniques you can prepare metal carbonyls from. And also we'll be talking about after the metal carbonyl is present in any metal, like any carbonyl ligands present in metal, how can you activate those metal carbonyl complexes? Also, what are different reactions that metal carbonyls can participate in? And all of those we are going to study in this chapter. This chapter is quite important for organometallic point of view, because carbonyl as a ligand is present in almost all the, like, majority of the complexes. I hope I'm quite clear with what I'm teaching. And so, thank you.